right. So last time we finished up talking about coordinates with respect to a basis. So that's the last thing that we're going to talk about in chapter, I believe it's chapter 4. So I did make your assignment over 4.7 due on Thursday, as well as the assignment. I think the other assignment is also due on Tuesday. Is that right? Doing tomorrow for 4.6. 4.7 should be really short. It's only a few problems, and it's all finding coordinates relative to a basis. So I think I have only 4 problems on it, so I don't think that'll take me very long to get done. Since it's all the same type of problem. So, going forward then, any questions at all before we get into some new stuff? Okay, so let's go ahead and start up chapter 5. Chapter 5, we're going to add a new operation to some vector spaces. So throughout, everything was already assumed to be a vector space. So again, when we have a vector space, we already have an addition defined. We already have a scalar multiplication defined. And we have all those vector spaces axioms that are satisfied. Pardon me, goodness. We're going to add a little bit to that. So but like I mentioned, we already have a lot of structure when we have a vector space. So we're going to add a little bit more structure to that. And the idea comes from what you think about when you think about vectors, generally speaking, especially maybe from a physics perspective. What two quantities do you usually associate with a vector? Or the kind of the two things they tell you that you have associated with a vector? You think I'll just start drawing them. What kind of two things do you associate with a vector?
Direction.
Yeah, direction, right? Which way is it going, and what else? Now, magnitude, how long it is, right? How big it is, how long it is, and which way is it going, right? So that's exactly what we're thinking about when we're talking about an inner product. The main purpose for assigning what we refer to as an inner product is to assign an idea of magnitude, assign an idea of length. We're gonna. Oh. You almost said that. So that's one idea that we have is assign an idea of a length of a vector. So you do this in our Euclidean vector spaces, our Rn vector spaces, in a usual way. And I'm going to add to this list here in a second. But let's just take a side trip here to talk about what we mean by assign a length. When you have your Euclidean vectors, let's just do it in 2 dimensions to start with because those are easier to draw. If I think about a length, we usually think about everything being in a standard position, right? You think about it being starting at the origin is your initial point. There's some terminal point out here, xy. And then we can talk about the length of that vector literally just being the length of that line segment. And we can do some Pythagorean theorem ideas on that. The length of your, I'll say this bottom side here is x. The length of that up and down side is y. Technically, I probably should put absolute value of x and absolute value of y there in case my point might be in a different quadrant than the first quadrant. But when we find the length of our other side, we do, of course, square root of the sum of the squares, right? Now, if we have this notion of an inner product for Rn, we can also assign a length of the vector using the inner product. So let's talk about the inner product just briefly. When we have what we talk about as an inner product or a dot product in R2, which is where I'm looking right now, if you have an x1, y1, and an x2, y2, and I have that dot in the middle, so usually what we call a dot product. You probably know from other classes that you do the product of your x coordinates, the product of your y coordinates, and add them together, right? For a dot product. I can express length in terms of this dot product. notice that if I take the vector xy and dot it with itself, I get x squared plus y squared, right? So the length of this vector here can also be thought of as the square root of, I'm just going to denote the vector by a v. I can do the square root of the vector dotted with itself. And that also gives me the length of that side, right? If I take xy and dot it with xy, I get x squared plus y squared. Take the square root of that, I get the length. So this is, generally speaking, if I have a dot product defined already, I can talk about the length of the vector by doing the dot product with itself and taking the square root of it. That is, on the right-hand side is our notation for length or magnitude of a vector. Also, it's called the norm of the vector. And typically I say norm rather than magnitude because norm only has one syllable and magnitude has three. So they all both mean the same thing. So the norm of V is the square root of the dot product with itself. Notice there's nothing special about the fact that, the special part is that we define this as Euclidean distance and recognize that we can do the dot product with itself to get us that. But there's nothing special about it if I already have the dot product defined. I can define norm in this fashion for any dot product that we might come across. And we've already seen that we've treated other things like they're vectors rather than just Euclidean vectors, right? We've done polynomials as vectors, we've done matrices as vectors, we've done functions as vectors, and there might be other things that we might want to treat as a dot product, that aren't just taking the sum of the product of the coordinates. All right, but that's one purpose of doing an inner product. Another idea, and it comes along with the norm as well, is to assign a distance between vectors. How far apart are they? So again, let's lean on Euclidean. Let's say I have an x1, y1, and I'll call this my v. And I'll do x2, y2 here and call this w. I want to know what the distance between these vectors is. And when we talk about distance between vectors, what we really mean is distance between their, in the Euclidean sense. When we say distance between vectors, we really mean distance between their terminal points. Because hopefully it's pretty obvious that the distance between points down here closer to the origin is smaller than the distance the farther we get away from the origin, right? So when we say distance between vectors, we really, in the Euclidean sense, we really mean distance between their terminal points. Well, if we use some geometry notions, we can figure out the vector here between these two by doing what? Think about your geometry from different things maybe you've done in physics class. How can I express this vector here where I start at this point and end at this one? Yeah, it's a difference, right? It's the v minus the w, right? In that case. So do you think how we might be able to define the distance between the two vectors at this point? In terms of using vector language, can we talk about how we can find the distance between the two vectors? What vector might we want to pay attention to if we're looking at the distance between v and w? The v minus w, right? If I want the distance, then what do you think I might want to use in terms of v minus w? It's magnitude, it's norm, right? So we can define the distance between the two vectors as the norm of their difference And again, in terms of dot product or inner product language, we can define that as the square root of the inner product or dot product with itself. Now, v minus w with itself. By the way, you can check that it actually works, right? Because the distance, you can check that it works in the Euclidean sense. V minus w would be x1 minus x2, y1 minus y2. So the length of that would be x1 minus x2 squared plus y1 minus y2 squared, and then take the square root of that. Right? So you can check if that really does work. But notice again, I'm trying to write this in terms of a dot product or an inner product. Inner product is the same as dot product. It's a different word that we use. Because again, if I can define an inner product in a different way, I still want the same properties to hold and the same ideas hold. What's the length of a vector? What's the distance between vectors? Those kind of things. So far, so good? All right, so length, the notion of length, the notion of magnitude is one thing that we want. The notion of magnitude helps us assign a distance between those two vectors. The other quantity that you told me a minute ago that is also that you think of associated with vectors is direction, right? Direction would be an angle idea. So we can also use inner products to assign an angle between vectors. And we'll come back to angle between vectors in a little bit when we get our formula for it. Okay. But in any event, these are kind of the things that we want to use an inner product for. We assign length and assign angles and play with those ideas. Angles help us determine whether or not vectors are perpendicular to one another. Perpendicularity is a nice property. We call it different. We give it a different name later on. But perpendicularity is a nice property for vectors to have. It allows you to write things a little bit more simply as we go through it. All right. So what do we mean by inner product, and what kind of things does it need to satisfy? So before I get into the axioms, we need to actually define what we mean by an inner product. So it's this function that's going to take two vectors and spit out a number. That's the idea behind inner product. It has to take in two vectors and it's going to spit out a number. So as a lead into our list of axioms here, we're going to let V be a vector space. And then we're going to let this function, again, the inputs are two vectors, and the output is a real number for our purposes. It may be the case that in other applications you might get out a different type of number. You might get a complex number out, for example. For our purposes, everything's going to be real numbers coming out of this thing. Okay. So the way we define the function, I know I've used dot so far, but another standard way to define inner product is with angle brackets and then put the vectors in between them. So this is the notation I'm going to use for the function. So just think of this as like an F. Okay, this is just my function. Okay, I'm just using notation for function. This function is going to go from the set of all ordered pairs of vectors. Okay, so again, I told you that the inner product takes in two vectors and spits out a number, right? So that's all this is saying here. Remember, this is our notation for the set of all ordered pairs, right? It's Cartesian product. It's going to go take in an ordered pair and get out a real number, okay? So this is just our notation for functions. All I'm saying, I'm just writing it in shorthand. Then we say this function is an inner product on V if it satisfies these four axioms. So let's just think about some axioms that we might, or some things that we might want to be not. Let's think about some properties of this function that might be nice to have. Okay. So, what's a nice property of a product that, say, numbers have, say, polynomials have, but matrices don't have, as far as the product goes? What property does a product of two numbers have, usual product of two polynomials have, and so on, but matrices don't have? What property of multiplication does numbers have that matrices don't? Yeah, the commutativity, right? Being able to go back and forth. So that's going to be our first inner product axiom, is that if I take the inner product of two vectors, the order doesn't matter. Okay. So the inner product is commutative. I can do the inner product in either order. It doesn't matter which order you do it in. Another vector space axiom that might be nice to have. Well, this one actually works for any product that we've talked about so far, pretty much. Whether that be just how numbers work with respect to addition, or products work of numbers with respect to addition, or scalar multiplication with respect to vector addition, or any of those kind of things. Distributivity is a nice thing to have, right? Distributivity over sum. Okay. So the second one is if I do V and dot it with, or do the inner product with W plus X, I get the inner product of V and W and the inner product of V and X. So this just says that I can distribute the inner product over a vector sum, which is probably something you've already done if you've done dot products before for Euclidean spaces in Cal 3. Right? Assuming you've done something along those lines. And the next one we're going to talk about, it talks about how scalar multiplication behaves with respect to the inner product. And basically it just says that doesn't matter where you put the scalar, you get the same answer. So I can do the inner product of the two vectors together first. And then do the scalar multiplication. I can do the scalar times the first vector, and then do the inner product. And actually, I didn't need to write this second part. This second part follows from commutativity. But you can also put the scalar on the second vector first, and then do the inner product, and you'll get the same answer every time. I don't really need to write this last one as far as one of the axioms go, because again, if it's commutative, if the inner product is commutative, this one here, I could have commuted the W and the V first, and then put the C on the W, and then just recommuted. So I didn't need to write the last one as far as part of the axiom. All right. These are things that you would expect to have happen. I'm going to write the last one here in a second. These are things that you would expect to have happen if you've already looked at dot products of Euclidean vectors, right? Certainly, I know I've done it for R2. For Rn, we can just extend it. But if you've done something like this for three-dimensional vectors, say, if you took your x1, x2, x3, and dotted it with
y1, z1, and dotted it with x2, y2, z2. If you've done this type of thing before, this is going to be x1, x2 plus y1, y2 plus z1, z2. And if I could actually write today, that would be helpful. If you do it the other way around, all it does is flip your products, right? But these are all just real numbers. So these two things really are equal, right? So again, if you think about how your usual dot product works in Euclidean spaces, these properties aren't huge surprises, that they are things that we would like to have or things that we should have, right? At least I hope it's not a huge surprise. Basically, again, these are typical product properties that you like products to have, right? You like it when products work in either order. You like it when products distribute over sums. You like it when products are associative, which is what this last one really is. At least I assume you like that. Okay. So the last part, this last one is where we actually start getting that notion of length in here. So the last one says that if you take an inner product of a vector with itself, when I take the length, my goodness, can I write a freaking greater than or equal to sign? When I take an inner product of a vector with itself, I get something that's always positive. Greater than or equal to 0. Okay. Now again, if I want to talk about length, this is important, right? Because how are we going to define length of a vector? What am I going to do with that dot product of the vector with itself? Take the square root, right? So I better get something that is non-negative, correct? And the second part of this is the dot product of a vector with itself, or the inner product of a vector with itself, is 0, the number 0, if and only if the vector you started with is the 0 vector. In terms of length, what does this say? Think about it in terms of length. What does this particular property say has to be true? So, well, there is a length that's length 0, but how many have length 0? Only one, right? There's a unique vector that has length 0, correct? That's what this says. The only vector that has length 0 is the 0 vector. That makes sense? All right. So these are the 4 inner product axioms, okay? The first 3, again, I don't think are really big surprises, okay? This is how you, with the exception of matrix multiplication doesn't satisfy the first one, this is what you're accustomed to products satisfying, right? You're accustomed to products working in either order, products distributing over sums, products being associative. That's essentially what that is, right? All right. However, if you want to check if something is an inner product, then we need to make sure that those 4 axioms are satisfied. Now, typically, those 4 axioms are pretty straightforward to check, but we still have to check and make sure that they're correct, or satisfied before we can start using things as an inner product. All right, so let's look at this one. And I'm purposely doing an example that's not Euclidean space because hopefully you're familiar with Euclidean space. Those are pretty straightforward. So what I would want to do is start introducing other notions of inner product that aren't necessarily what you're used to and show that we still can have the same types of notions. So let's look at this. P2, again, is our set of polynomials of degree 2 or less. and we're just I'm identifying two polynomials in that space. We're defining a product of those two polynomials to just say take the corresponding coefficients, multiply those together, and then add them. Okay? All right. So let's talk about, this is an inner product. So let's show that it really is an inner product. Because I dropped things. So first thing is that we need to show that the inner product is commutative. Well, the inner product of P and Q is defined as product of your x squared coefficients, x coefficients, constant terms added together. Work it the other way around. What do we get if I want to do the inner product of Q of x with P of x? Yeah, good. A1 A naught, B1 B naught, C1 C naught. Everything here is a real number because we're doing polynomials with real coefficients. Doing polynomials with real coefficients. We're multiplying real numbers together, adding real numbers together. So what could I say about those two expressions? They're equal, right? So these really are equal to each other. So that first axiom of inner products holds. Let's introduce a third polynomial here. I'll call it R of x. I need to show that the inner product distributes over sums. If I do the inner product in this order, what do you do first? Okay, so we're adding the two polynomials together. So rather than the multiplication, the other one's going to be plus, right? So this one doesn't change. I just write them out longhand here and use the correct coefficients. Notice that your A's get added together for the x squared term, your B's get added together for your x term, and your C's get added together for the constant term. So we would add the Q and the R together first, and then we would multiply, right? So what do we get when we multiply these, or take the inner product of these two things? Yeah, same for the other two, and they're all added together, right? The way the inner product is defined here is that it says take your A naught, or sorry, take your coefficient on the x squareds and multiply them together. Take your coefficients on the x terms, multiply them together, take your constants, multiply them together, then add everything, right? What if we break it up the other way? What if we do P, inner product of P and Q plus the inner product of P and R? What do you get here? Yep. Again, taking a product of your x squared coefficients, product of your x coefficients, product of your constants, add them together. Same thing for the second pair. Are these two expressions the same? Yeah. If I distribute these across, they can see that that's the same thing as that, right? So these really those two are equal to each other. So axiom 2 holds. Yeah.
What if the first px and the second comes out?
Here?
Yeah. I see 3 different issues.
This is what the axiom that we're trying to satisfy, right?
Yeah.
All right, so notice that. So we did p of x and then q of x plus r of x. It says p of x, q of x, p of x, r of x. Yep. I need it in both places to verify the axiom. We would do 3 the same way. I'll leave 3 for you to check. 4 is a more interesting one. 3 is just a matter of playing with the numbers again like we just did. I'll leave 3 for you to check, but let's look at 4. 4 says that if you do the inner product with itself, you have to get non-negative. That's the first part, right? Right? So if I do the inner product with itself, it has to be non-negative, right? This is what we need to check. What do you get when you do the inner product with itself? Yeah, you get a naught squared plus b naught squared plus c naught squared, which is definitely non-negative, right? We agree with that? The second part says that the only way that we can get the 0 as the inner product with itself is if we use the 0 vector. Well, what's the only way this can possibly equal to 0? What's the only way that a naught squared plus b naught squared plus c naught squared can equal 0? What has to happen? All of them are 0, right? So your a naught squared plus b naught squared plus c naught squared equals 0 if and only if a naught equals b naught equals c naught equals 0, right? The only way to get the sum of squares to equal 0 is that they're all 0. Everything's taking place in the real numbers here, right? Right? This is why we have polynomials with real coefficients, okay? And so this is if and only if p of x really is the 0 polynomial. Right. So this really does satisfy the axioms of an inner product. Notice that this shouldn't have been a huge surprise, because what are we really treating each of the coefficients as? And we're treating it just like it's a vector, aren't we? Just like it's a Euclidean vector, aren't we? We're just treating the x squared coefficient like it's the first component, the x coefficient like it's the second component, the constant term like it's the third component, and doing a regular old dot product of Euclidean vectors. So this shouldn't have been a huge surprise that we really did get this satisfied. All right. Anyway, let's try a different one. Let's do the next example. Does this one look like a regular old Euclidean inner product? No. This one's taking continuous functions on the interval from a to b and saying we're going to define the inner product of two vectors to be the integral of their product. That's different, right? Feels different. Okay? This is different. This is definitely different. So, but again, hopefully it's pretty obvious that commutativity works, right? We agree it's pretty obvious that the inner product will work either order. Because the product is really taking place in here. P of x times q of x as polynomials is the same thing as q of x times p of x, right? So the first axiom is not too big of a deal. What allows your second axiom to work? Yep, exactly right, Ian. So we can split the integral up, right? This is the definition of the inner product of p of x with the sum of q and r, right? If you distribute your p of x and then split the integral with the plus sign, this becomes p of x q of x dx plus integral of p of x r of x dx, right? That's a Calc 1 idea. And get p of x q of x for the first one and p of x r of x for the second one. So that would be verifying axiom 2 actually works. Does that make sense for everybody? That one okay? So notice that we're using the property of integrals here that allows us to split up over sums. Axiom 3 has to do with constants. What property is going to allow you for that one to work? Yeah, you can pull constants out of the integral or move it back inside the integral, right? So that's why 3 is going to work. So notice that both of those are just the way that integrals work. So the fourth one's going to be the more interesting one. If we do the inner product with itself, that's the inner product with itself. How do I know that that's non-negative? Yeah, the square, right? If I square the square the function, it's always going to be above the x-axis, or it could touch the x-axis as well. But certainly, if it's not on the x-axis, it's above it. Definite integral counts area under the curve above the x-axis is positive. So this certainly is never negative, right? Because the function is never negative. So this is greater than or equal to 0. Since your p of x squared is greater than or equal to 0 on the interval from a to b. The next part is a little trickier. Remember again, what do we have to show for the last part here? That the inner product with itself is equal to 0 if and only if what's true? The vector is 0, right? So I need to say that this is equal to 0 if and only if the function itself is identically 0, always 0. There's not a lot to show here. It's more of a concept idea. So let me talk about what I mean. If you were to draw a function like this, let me put it on the board. If you were to draw a function like this, so let's say I had my a here, my b here, and my function was along the x-axis, except here at this empty spot, and then I put it up here. What would the integral of that be? It's 0, right? Because at a single point, the integral is 0, correct? Okay. So this integral would also be 0. Is that function the 0 function? Is that identically equal to 0 over the entire interval? No. Okay. Why is that not a worry for what we're doing here? What kind of functions are we talking about? Continuous functions, right? Do I allow this when it's continuous? Is this continuous? No. Okay, there's a jump, correct? Okay, so this is equal to 0 if and only if p of x is identically equal to 0. Again, if we want to emphasize that we're saying the function's always equal to 0 and not just equal to 0 sometimes, we use that equivalence bar, that extra bar on there, like it's an equivalence relation idea. Okay, this is because p of x is continuous. If we weren't allowing continuous functions, that wouldn't work. Okay. What this tells me is that I now have a vector space of continuous functions on the interval from A to B that I can define an inner product on. However, if I just said do all possible functions on the interval from A to B, I couldn't define an inner product on it this way. It wouldn't work. Because there's a function that has an inner product with itself that would equal 0. That's not the 0 function. So that wouldn't be an inner product on a set of all functions on A to B. Continuity is important here. Okay? All right. This particular inner product is important in lots of different applications. In particular, if you're trying to approximate nasty functions with continuous functions, this particular inner product pops up. I hope we'll get to it in this class, but I know we'll get to it in numerical. So you'll get to hear about why that's true if you're in numerical. If you're not, hopefully we'll get to it this semester. May or may not, this depends on what time we have. But if you've had statistics at all, you've probably talked about least squares. This allows you to do least squares ideas on things that are functions rather than just kind of doing dots everywhere, trying to approximate the dots. Anyway, this particular inner product is important. What is the gist of that information? All right. So let's talk about a few of the properties of inner products, and then we'll do some computations probably next time with weird inner products. Notice the first one is not a huge property or not a huge surprise. At least I hope that you would expect it in a product property. This one says that if I multiply by 0, I get 0. Right? If you want to verify this, what kind of standard, I'll call it a trick, it's not really a trick, what kind of standard trick do we use in order to be able to prove this kind of thing, do you think? Yeah, so probably the standard trick that we do is just rewrite the 0 as 0 plus 0, right? Done this before, correct? What does that now allow us to do on the right-hand side of the equation? Well, in terms of the inner product, what does it allow us to do on the right-hand side? Yeah. We can distribute, right? Now, our inner product space axiom will have the distribution on the left-hand side, right? It had V, the product of V and W plus X on the right. Why do I know that I can also distribute it from the right to the left? What allows me to distribute the other way, too? Commutative, right? Because the order doesn't matter, correct? Now, everything here is a real number, so what do I need to do to finish this off? Yeah, just subtract the inner product of 0 and V, and we'll get this. Subtract the inner product of 0 and V from both sides, and I really do get what I wanted. Now, be careful. When you do the inner product of two vectors, you get a number, right? This is the 0 vector. This is the 0 number here. No vector here. basically for A, we used B, so I probably should have proved B first. But you already told me why this works. If you wanted to go do it out longhand, we could. But you already told me why this works. How do I know this distribution is going to work? Wait a minute. That is exactly what I wrote, isn't it? Apparently, the other book that I used for this had the distribution go the other way. This is the axiom. Really, I meant to do it. The other way around. This way. I'm going to do that distribution. But why does that work? Commutative, right? This is equal to that, right? Which would then equal this from your axiom and then go around this way. This is what I really meant to do. When I put these together before, the book I used had it the other way, the axiom the other way around. In any event, that's what I meant for it to do. And then for part C again, I wrote it as part of the axiom, but I told you we didn't have to write it as part of the axiom because, again, what are you going to use to prove this? It's the commutativity part, right? Flip around your K, V, and U. Put the K in the first component. Take the K out according to the axiom, and then flip it back around for the commutativity. So that really is just commutative. Basically, it's just a consequence of the third axiom and commutativity. So again, just to write it out, longhand, this would be KV with U. Then the third axiom says that you can pull out the K, and then commutativity just gets you back to that spot. One reason why I'm drawing arrows here, which I'm guessing most of you won't ever see again anyway. One reason I'm drawing arrows here is this is an example of what we would refer to as a commutative diagram. If I think about my arrow going this way or going this way, I can take that path from here to here, or I can go this path this way from here to here. That's what a commutative diagram means. And they pop up in lots of different algebraic contexts. I know we're out of time, but just real quick, to get distribution over subtraction rather than addition, how can you rewrite U minus V and then use your distribution over addition property? How can I rewrite U minus V? Yeah, U plus negative V. And negative V is the same thing as negative 1 times V. We've already proven those things, right? Right? So you can do your distribution and then pull out your constant. All right. So anyway, those give you some vector inner product space properties. So we'll start doing some of these other notions of distance and length and angle on Wednesday.